Question D of part 3, or question 3 of part D, wait. Anyway, you know where we are. Show that when the switch is closed, the stored energy will change by a factor of P over P plus 1. Comment on the role, that was stored energy, of the role of the resistor when the switch is closed. Well, the role of the resistor is easy. The energy that's lost is lost as heat through the resistor when the current flows. So let's consider that part dealt with. The more trickier part is this here, finding the stored energy will change by a factor of P over P plus 1. So what we have to do is we compare the initial stored energy to the, or EI if you prefer, to the final final energy and compare the two. So energy in capacitors is half QV. V is problematic because the voltage changes and we would rather have that in terms of, say, the capacitance, which doesn't change, and Q is the total charge, remember, so that doesn't change either. We've got Q equals CV, and if we're dealing with the initial, we're only concerned with C1. You'll have to look back at the previous questions or have a tab open in your browser with the questions open on it. So you can follow this. So we want to get rid of the V, so it's V equals Q over C1. So we can substitute that in over to here, and we have half Q squared over C1, or we might just call that Q squared over 2C1. Okay, so that's our initial energy. Let's put a box around that so I can find it easily later on. Our final energy gets a little bit trickier, and the charge is divided up over both of them, but the total is still the same. So what colour? We'll go to blue, light blue. So final energy is still going to be according to the same kind of idea here. So it's half Q squared over the capacitance, but this time we've got the capacitance has changed. Remember, the capacitors in series, as this is, they're added as the 1 over the one plus 1 over the other. Oh, sorry, they're in parallel though, aren't they? Tricky one, really. I guess it's operating like it's a parallel circuit, because, well, yeah, it is. If you're looking at the voltage and all that kind of stuff, it's a parallel circuit. But in any case, the capacitance this time is going to change to C1 plus C2 because it's in parallel. So that's what we're going to throw into here. Q is still the same because it's the total charge. If you like, this is the total energy in the circuit is total charge over total capacitance. And the change will come out as a factor of P, because in C2, remember, C2 equals C1 over P. So we're going to have a little awkward kind of mathematical thing going on there. Let's do this anyway. Q squared over 2 C1 plus C2. And that's going to give us, substituting this in now, we've got Q squared over 2 C1 plus C1 over P. Okay. And that's just looking a little bit awkward because remember we're aiming for that P over P plus 1 thing. So I might just drag this out over here and deal with that separately. If we factorize that, we've got C1 over 1 plus 1 over P, which we could rewrite, because this is awkward on the bottom, so just go with me here for a second. We could rewrite it as P over P plus 1 over P, because P over P is equal to 1. That gives us a common denominator to deal with, so we can call that just P plus 1 over P. So C1 C1 is P plus 1 over P. Okay, so that gives us something to deal with back over here. and we can have, I'll go back to my blue, is Q squared over 2C1, and then we've got this P plus 1 over P in here. So remember, if you divide by a fraction, it's the same as multiplying by the inverse. So this gives us Q squared over 2C1 times by P over P plus 1. And that is kind of cool, because that's exactly what we were aiming for. This is the final energy, remember. Final energy changes by a factor of P over P plus 1. So our initial energy was, where are we? Going back to the red. Our initial energy was this. Okay, E0 equals Q squared over 2C1. Yet in our final, remember this was the final energy, gives us Q squared over 2C1. So that's the same as our initial energy. And there's that factor by which it's changed. Okay, that is awesome. That's a really awkward one because of that fraction on the bottom of the fraction and how we arrive at it. There's a lot of important things that you need to take into account for this. One is that that charge is the same, and that your capacitors are added as if they are in parallel. Okay, because if you go back up to the diagram, I think did I sketch a diagram? I don't know if there's a diagram. Okay, here's the diagram just so that you've got it. One capacitor, a resistor, another capacitor, and you've got the switch that closes here. This was C1 with a charge on it initially and a voltage across it, and as you close the switch, C2 gets some of the charge, but they are in parallel in this way, not in series. If you added them in series, that seems like it would be quite an awkward solution. You can do it and see what you get. Yeah, but remember there's no power supply in this, so you can deal with them as if they're in parallel. It's just a little bit of a trick of it, I suppose.